So, welcome all of you. We have been discussing about heteronuclear correlation experiments. We discussed at stretch in detail about single quantum correlation, where we are going to do an experiment where heteronuclear spins which directly one bond coupled will be correlated. For example, carbon 13 directly bonded to proton or nitrogen 15 directly bonded to proton. See, it's such type of experiment, carbon 13 proton HSQC or carbon 13 nitrogen 15 proton HSQC. We understood how we can do that, how we can interpret the spectra, everything. Why we are not going to see the signal? Because of the long range coupling which are present in the molecule in HSQC. We calculated the intensity and saw that in such a case the intensity is too low to be detected in the HSQC. We understood that, and we also interpreted a lot of spectra. Then to go further, but if you want to detect correlation, the long range correlations like proton coupled to carbon which are 2 bonds or 3 bonds away, 2J3J coupling if it is present, there is an advantage. In such cases, remotely bonded carbon to proton like quaternary carbons, CO carbons, they also can be detected. So, this type of experiment is called heteronuclear multiple bond correlation experiment. In the heteronuclear multiple bond correlation experiment, what we do is we have a filter for long range correlation delta LR, whose value is set for the long range coupling of the order of 5 to 10 hertz. And then we will allow only those correlations, and the correlations coming because of the long range coupling, one bond couplings are suppressed. And for that we use a filter. There are two types of filters in HMBC. One is filter J accept and J reject. J accept is a filter like delta LR, where long range correlations are allowed through, whereas one bond correlation like HSQC cross peaks, they are all suppressed. That is another type of filter. For this we have different types of filters, not just one filter. That filter can be utilized in such a way we can allow only long range correlation and suppress the one bond correlation. One such filter for that is a bird sequence. I told you about the bird sequence. Bird sequence is a very simple sequence. We saw in the bird sequence what is going to happen is we have 290-degree pulses separated by a delay, and in between a 180 pulse on the proton channel, and the carbon 13 also we have a 180 pulse, and the delay is set to 1 over JCH. In this case what is going to happen is vectorially with the picture we saw that this bird sequence has an effect only on the carbon 12 attached protons, which would selectively invert them, whereas this sequence has no effect on carbon 13 attached protons. This is what we saw. It will selectively invert only that, and this is the effect of the bird sequence. The effect of the bird sequence is carbon 12 proton is selectively inverted and carbon 13 attached thing will continue to evolve. And this is what we saw for carbon 13 one night, the chemical shift will refocus, and after a 2 delta period we saw the doublet vectors which was along the y axis for the carbon 13 attached will return to z axis, and which is going to be detected by the final proton pulse. So, okay, that is what is going to be detected. For carbon 13 spin, bird has no effect. That is what you should remember. And this is the HMBC sequence with bird. Everything remains same. We have LR, and in between these two LR a bird sequence is put. And bird sequence, as I said, selectively invert only those protons remotely bonded to carbon 13 2 bonds 3 bonds away, and does not affect the protons which are directly bonded to carbon 13. So, then this achieves the selective refocusing of 1JCH, since only carbon 13 experiencing a 180 pulse, but defocusing of all long range couplings, because 1JCH in the bird sequence is set for 1JCH, the delay delta. So, it refocuses all the correlations coming because of NJCH, for which both 1 and carbon 13 experience net 180 pulses. That is what it does. It defocuses the remote and then refocuses the 1 by JH. Of course, 1 JCH values can vary. It is not constant. 1 JCH can be 150, 200, 250 depending upon the type of molecule we are looking at. This can affect the efficiency of this approach because we set the delay for one value in the bulk element. But if the value is different, that can cause some issues, complications will come. So, addition of a subsequent 180 degree carbon 13 pulse followed by 1/2 this period of delta 1 refocus of only one bond coupling that have passed through a bulk filter. This is another way of doing it. What we do is we apply another 180 carbon 13 pulse followed by short 1/2 JCH in the delta, which refocuses those one bond coupling which did not get filtered out because of the bulk. That can be done. So, since 1 JCH are field focus, they no longer generate multiple quantum coherences and do not contribute to final spectrum. This is what happens. Why we are not? So, what is going to happen is we suppress one bond coupling which do not contribute to the spectrum because we use the filters. Okay, there are varieties of filters. Another thing is phase alternation of 180 pulse. That is another way which can effective suppression of one bond correlation. That is also possible. We can do that. One more experiment is there, another improved version of HMBC. It is called constant time experiment, constant time HMBC, eliminating proton-proton coupling in F1. Is a very simple thing. How do you do? Do not allow couplings to evolve in the T1 period. Keep it constant. If it does not evolve, then it is as good as decoupling, removing. The 2 JHH, for example, JHH evolution can be suppressed if the modulation of the signal in T1 is suppressed. How do you do that? T1 gets modulated, we get a modulated signal when we keep incrementing the T1. Instead of that, we can keep it constant. How do we do that experiment? But we need to increment the T1 to get the FID. But we do in a very tricky way. I will show you that. What we do is, if the evolution of JHH is there in the T1 dimension, it gives peak broadening in both HMQC and HMBC. Usually visible due to low resolution, usually not visible due to low resolution, but that gives us to broadening. But JHH evolution is due to modulation of the signal as a function of the T1 period. Evolved because there is a modulation. What we do is we stop this modulation. Somehow we keep the evolution constant, evolution time constant. Then we can prevent the JHH modulation. For example, look at this one, constant time period. Here delta constant time, this is called constant time period, delta CT, that is always kept constant. The delay is set to a maximum value that T1 period will attain in the experiment. As you know, T1 keeps incrementing from a small value, we can increment to some value. That is the maximum value, keep it constant here. Okay, that is what. And then that is called delta CT T1 maximum, this one. And then this one, 180 pulse, in between we can move it forward or backward, either way. So that this time is always remains constant. You understand? So we can keep this constant, but we can move this way or that way. Whereas this LR is constant, this is before and after, that is constant. This is after this one. So that is always kept constant. This is a constant time. This is an experiment. Delta CT minus T1, we can keep increasing it as T1 increases. So the total period remains constant. You have to maintain this one constant and this one keeps changing. That is what we do. And this variable delay can be reduced from maximum value to 0. First delta CT we keep it constant and this keeps on subtracting this T1 delay, so that it comes to 0 as T1 is incremented from maximum of T1 value to 0 value. So delta Ct is the one which is maintained. And during this process, what happens? The proton-proton coupling evolution do not get modulated at all. Do not modulate the detected signal. This is one constant time experiment. Identically, we can do this constant time experiment in HMBC. That is one way. So, there is another improved version of this constant time. All right, there are so many such experiments, so many modifications are there. Several modified versions of there, like impeach is there, pendant is there. They are all different pulse sequences. Let us not discuss too much about those things. But please remember, we can use constant time HMBC. We can also use bulk element to selectively invert the protons or touch the carbon toll. All these experiments are improved versions, so that 1 bond 1JCH is always suppressed. Long range NJCH are all allowed through. That is the filter which allows, and the others are reject filters will stop that. This is the basic idea of any HMBC pulse sequence. With this, now we will try to understand the interpretation of the peaks in HMBC. Start with the same molecule which we took earlier. We will look at the F2 coupled HSQC, carbon 13 proton coupled. Where does HMBC gives cross peak? We understood HSQC, where does it give cross peak? Both in coupled and decoupled. Where does HMBC gives? We will understand. Remember, in the F1 dimension, if the chemical sheet of carbon A is there, it gives correlation to the remotely bonded proton, not for the one bond. That is HSQC, you know that. So, we suppress that. It gives correlation to long range proton. So, if in the HMBC experiment, in the F1 dimension, if you get a chemical sheet for carbon A, in the F2 dimension, it pertains to chemical sheet of proton B, not proton A. This is this thing. This is the difference between HSQC and HMBC. In HSQC, if it is carbon chemical shift, same proton chemical shift which is attached to it. Whereas in the HMBC, if you look at the carbon chemical shift of A, it gives correlation to proton which is 2 or 3 bonds away. Here 3J CAHB is there. See, if you go to carbon B in the F1 dimension, chemical shift is carbon B. In the F2 dimension, it is going to be proton chemical shift of A, not B. B is CBHB correspond to HSQC. But now carbon B chemical shift correlates to proton A chemical shift, which is 3J CBHA. That is the type of peaks we get if you do coupled HMBC. Let us see the spectrum here. This is F2 coupled HMBC. Now I am seeing the proton carbon chemical shift here, go across. I am not seeing correlation here. That is one bond. We are suppressing that. That is HSQC cross peak. Come here. It correlates to the remote proton. And this proton is a doublet. Why? Because of one bond JC, I'm sorry, not one bond, 1, 2, 3 bond JCH coupling. 3 bond carbon proton coupling is there. That is a doublet. And the center of this doublet corresponds to chemical shift of proton HB. What about carbon B? Where does it correlate? Carbon B also is a doublet because this is correlating to proton A, proton HA. As a consequence, long range 3J CBHA coupling is there. So, that is why that is also a doublet. So, along this axis you get carbon chemical shift, along this axis you get proton chemical shift. This is the F2 coupled HMBC spectrum of these molecules. Please see the difference here. In HSQC we are seeing the cross peak of Ca to HA. Cb to Hb you are seeing Cb to Hb here, but in HSQC, that is HSQC, in HMBC, Ca is correlated to Hb, Cb is correlated to Ha, remotely bonded, 2 to 3 bonds away. This is what it is. The same thing if I do the decoupling, what happens? I told you, HMBC is always recorded in a way which is coupled motion. We don't decouple it, I told you. Even if you say it is, if you want to do the decoupling, how do you understand that? simply break the coupling between 3 bond carbon proton coupling. So it is going to be a singlet. So if this axis is a chemical shift of carbon A, go vertically up, you get chemical shift of proton B, not A. Remember, this is A and proton B. Similarly here, chemical shift of carbon B, in this axis it correlates chemical shift of proton A. So they are cross correlation. See, Cb is correlated to Ha and Ca is correlated to Hb in the decoupled. Okay, this is decoupled. What happened proton-proton couplings in HMBC? Can it come? Why not? Exactly similar to what we saw in the HSQC. This Ca correlates to Hb. But what is Hb? It is coupled to this. When it is coupled to this, what will happen? It will be a doublet. That will be seen. So Ca is a doublet because of 3 bond coupling with Hb, plus it is also a doublet. Each doublet of the doublet, each peak of the doublet is a doublet because of coupling with CH proton. This is what is going to happen. So Ca will be a doublet because of 3J coupling with Hb, plus doublet of doublet because of HH coupling. That is what it is. This is what is in the F1 dimension, we are going to get chemical shift of A, and the F2 dimension it correlates to proton chemical shift of B, and it is a doublet of doublet with large coupling and small coupling depending upon which they are almost of the similar strength. 3J coupling of carbon proton and 3J coupling of proton proton. The pattern is a doublet of doublet. If you go to the other carbon, carbon B, it can correlate to proton A, 3 bond. But then what about this proton? It is coupled to chemically equivalent CH2 protons. Then it will become a triplet. So what will happen? First, this carbon is a doublet because of long range coupling, 3J coupling, and then each lane of the doublet is triplet, is a triplet because of coupling with CH2 proton. This is what you are going to get. HA, Cb is a doublet because of 3 bond coupling and is a triplet because of CH2 protons. So in the HMBC spectrum, in the F1 dimension you get carbon chemical shift of B, but in the F2 dimension you get proton chemical shift of A because of splitting of 3J and 3JHH. One is a doublet, other is a triplet, and this is how the pattern you get. Very easy. Look at this Ca carbon, it is correlating to Hb proton. Center of this correspond to chemical shift of proton Hb. It is a long range coupling, one of them maybe 3JCH, and then each of them is further split because of HAHB. Okay. So that is what Hb and CH proton, 2 protons are there. They are this is a doublet of a doublet. Whereas HA proton, if you look at it, this is correlating to carbon B, and the center of this correspond to HA proton chemical shift. It is a large doublet because of 3 bond CH coupling, but each of this doublet is a triplet, 1 to 1, 1 to 1, they are overlapped because it is coupled to CH2 proton. This HA proton is coupled to CH2 proton. As a consequence, it is going to be doublet of triplet, some overlap is there, and you will not be able to see all the multiplicity clearly. This is what you are going to see in the HMBC spectrum. See the difference between HSQC and HMBC. HSQC it was Ca was correlating to HA, Cb was correlating to HB here. But in HMBC they are all different. Ca correlates to HB, Cb correlates to HA. But the multiplicity pattern, what you saw in HSQC, what you are seeing in HMBC are similar. Only thing is in the HMBC you have a long range correlation and HSQC you have a 1 bond correlation, and in both the cases if you want proton couplings they all get reflected. This is what basically you have to understand. If you do the decoupling of the same thing, what is going to happen? You remove the carbon proton coupling, but HH coupling is present. So at the Ca chemical shift you have chemical shifts at the Ca, it is correlating to CB, I am sorry HB, which is a doublet because of this. You are removing this coupling, but this is present. That is what happens, it is a doublet. Same way here at the CB chemical shift, which is correlating to HA, that you are breaking, but this will be a triplet because of this, that is seen here. That is what is seen. This is the decoupled HMBC. This is what we are going to see. Then what about the terminal peaks like we saw in HSQC? We can try to interpret that. If you go to the CH2 carbon, CH2 can correlate to Ca proton, Ca carbon, and CH2 is this is correlating to HA. This is HA. This is the carbon of this one. It correlates to HA proton, and each of them is a one bond. Of course, CH coupling is also there, and because it is F2 coupled, you also have HH coupling. HH coupling is also seen. HH coupling is a doublet because of this proton. That you should remember. We are seeing this carbon, which has a long range correlation to this, and also this has this CH2 carbon, CH2 proton is a doublet because of HA. This is what you are going to see. Similarly, HB, along this axis you get carbon chemical shift. Exactly from the center if you go, you get proton chemical shift. Again CB, you are correlating with this proton we are considering is correlating to, I am sorry, this carbon correlating to this proton, and there is a doublet because of that, and that is what you are going to see. Of course, if you do the decoupling, you will make the carbon proton couplings, but you retain proton proton couplings. That is what happens. You are retaining the HH coupling here, both the cases. In both this carbon you will be a doublet, and this carbon is a doublet because of this. So HH couplings are retained. So we will look at the realistic example of HMBC spectrum of ethyl acetate. This is a simple molecule. Let us look at this. Exactly like we analyzed HSQC, same molecule I am taking, we will analyze the HMBC spectrum. How do you analyze HMBC spectrum here? Start with Ca3. Okay. Ca3 protons, which is marked 1, H1, it has a long range correlating with the CH2 carbon. These protons are correlating to this carbon, that is 2 bond coupling. What will happen? That will become a doublet. So we are seeing this one proton for correlating to the CH2 carbon is a doublet. Then what will happen? Each line of the doublet is split because of these CH2 protons into a triplet. This is going to be a doublet of triplet. But you see, this is a doublet, and you will see 1 2 1 1 2 1, 2 triplets are there which are overlapped here. We do not see that. Okay, and because of that it appears like a quartet. We have seen this multiplicity pattern when we were analyzing the proton spectra. So it is a doublet, and each of the doublet is a triplet because of CH2 protons. Okay, now go to the next one. Next one is CH2 proton. This is H3. This CH2 proton can have a long range correlation to what? This carbon, Ca3 carbon. It will make it a doublet. Yes, but then each of this doublet is a quartet because of 3 equivalent protons. So we will get doublet of a quartet, and 4 lines. See, it is doublet is here, and each line is a 1 3 3 1 1 3 3 1 1 3 3 1 overlapped here. It looks like a pentet. That is what happens. It is doublet of a quartet, is overlapped and appears like a pentet. And also if you see the CH2 carbon, this CH2 proton is also correlating to CO carbon. 1 2 3 bonds, 3 bond correlation is there. What will happen here? This is going to be, because of CH2 protons have a long range correlation to C4, it is a doublet first, and then each doublet line is split into quartet because of the coupling with Ca3 protons. See, again you get a pentate like you saw in the previous example, like here. Again it is a pentate because this is these two is correlated to this and this is also correlated to this. In both the cases, this proton will split this into a quartet. Exactly what you are seeing. Again it is a quartet where where some of the lines are overlapped here. Alright. What is the next one? Next one, if you see, we have to look at the other carbon, CH2 carbon. This is CH2 carbon. This CH2 carbon, and we have Ca3 protons here. Let us consider these protons. It can have 2 bond correlation with CO carbon. That is all. When it has a CO 2 bond correlation, what it will do? It will become a doublet. Okay. That is all. And no other coupling is there. HH coupling cannot be seen because nothing is there. This is not split by any other protons. So CO carbon, because of this, is going to be simply a doublet. Ca3 protons have a long range correlation with CO carbon and it is a doublet. Simply by using all this information, we can identify all the cross peaks. So now we know how to analyze coupled and decoupled HMBC spectrum of one of the molecules you have taken. We will take another example, a decoupled HMBC spectrum of this molecule. Now we will start analyzing the decoupled spectrum of this molecule. Its structure is given here. We will look at the molecule and we can even get the structure of the molecule if you analyze HMBC cross peaks. All the carbons have been numbered. Look at carbon 2. This carbon 2 shows 2 bond correlation to proton 3, 1 2 bond. See, it is carbon 2 here, proton 3, which is proton 3 here. See, carbon 2 is here. It is showing 3 bond correlation. That is what it is. And C3, carbon 3 shows 2 bond correlation to proton 2. That is all. Carbon 3 showing to carbon 2, carbon 2 is showing to proton 3. See, very interesting. Carbon 3 showing to proton 2, carbon 2 is showing to proton 3. There is a correlation is there between the two groups. Fine. Further you see C4 is correlating to H5, 2 bond correlation. Here C4 is correlating to H5. Also H5 is correlating to C4. These are isolated things. But if you look at one more carbon is there, which is not attached to proton, that is CO carbon. The CO carbon shows 3 correlations. One is this one, C1 to H4, C1 to H4. Other is C1 to H3, long range correlation, 3 bond, and C1 to H2 here, 2 bond. This is a very interesting thing. What did we understand? We saw only 2 correlations for this, C3 to H2 and H2 to C3 to H2 and C2 to H3. Similarly, C4 to H5 and H5 to C5 to H4, the H4. These correlations we observed. But in between there is a CO group. This CO group correlates to this proton, this proton and this proton. And there is no other correlation of this to this carbon and this to this carbon. All this observation, what do you understand? It conclusively tells you that C double bond OO, this group is sitting between H2 and H4 groups, between this and this. From the correlations we observed in HMBC, we can arrive at this structure very easily. Check the correlations, simply place the correlation what we observed and we know this is the structure of the molecule. Because this effect has to give correlation to this, this and this has to be between these two. It cannot be for the terminal group. And these two is We saw this is correlating to this and this is correlating to this. Similarly, this is correlating to this is correlating to this proton. With all this knowledge, we can get the structure. So, you remember how HMBC, because of the remote correlation for the protons to the carbons which are not attached to protons, CO or ipso carbons or in some carbons which are not attached to protons, quaternary carbons, we can even get the structure. We can completely even place the carbon which are not attached to proton also. So, that is the advantage of HMBC. It gives correlation to carbons which are not attached to proton through remote protons. So, we will take a simple example and analyze the 600 megahertz COSY, HSQC and HMBC spectra of ethyl ethoxypropionate. This is a simple molecule. This is a COSY spectrum. COSY spectrum identifies, you know how to analyze, start with one doublet, one of the diagonal peak, complete the square. Start with diagonal, complete the square. Start with this, complete the square. So, COSY identified 3 groups of spin systems. Fantastic. Go to multiplicity HSQC, you get 3 groups of CH2, red color, negative sign. There are 4, I think 4 are here, and only 2 CH3s which are add proton with a positive sign. These are all negative sign. That also fine. You can assign these things very easily. Then do the decoupled version of the same thing. HMBC, interesting thing you will see, C5 carbon gives long range correlation to 3 different protons, C5 to H6, H3 and H4. C5 gives to H3, H4 and H6. Very interesting. And C5, H6, 3 bond, all this the correlation we are seeing. If you expand this version of the same region and if you look at the correlation, we had C6 giving correlation to H7 and C2 H1. And remember, C6 is giving correlation only to H7 and C7 H6 correlates only to C7. This is a very interesting thing. We should see that. This is what is happening. Because H is correlated to C7, H7 correlates only to C6. We can see carefully the peaks here. This puts CH2 CH3 as terminal group. H1 correlates to C2 only, this H1, only to this and no other correlation. That gives me an idea that CH3 is a terminal group there. The C7 H7, I told you, C6 H7, C7 H6, that is form 1 correlation, and C2 H1 is also there. There are 3 correlations we get from this graph, which puts me, this is one group and this is another group. All right, you can continue this further. We can say H2 correlates to C1 and C3 and H3 correlates to C2, C4 and C5. And with all these observed correlations like this, C5 3 bond, C5 H3 2 bond, C5 H4 2 bond and these 2 bond 3 bond correlations, this is the structure we are going to get. We can place it easily. So, using HMBC, we can get even the structure of the molecules. Long range correlation gives you, puts you the carbons which are not attached to proton in a proper place in the structure. Why? Understanding the correlation of that carbon with the remote protons. This is what we wanted to see now. So, today we discussed about in this class lot about HMBC and HMBC pulse sequences, and I told you HMBC gives rise to, allows only long range correlation, suppresses one bond like HSQC cross peak by using filters, and we have different types of filters, and one such prominent one I told you is a Bird filter. We can also do constant time experiment to prevent the evolution of HH couplings like that. So, all these things varieties of experiments are possible. Finally, I just wanted to tell you by using Bird sequence also we can use that as a filter, and we can allow only long range correlations. And we took a lot of examples. We understood how to interpret the coupled and decoupled HMBC spectrum of some important molecules, how HH couplings are reflected in the spectrum, how they can be, CH couplings can be removed by decoupling, all those things. And we took simple example to show that 1 or 2 examples of the molecules, and by looking at the correlations, we can even place some of the molecules, some of the functional groups like C double bond O or quaternary carbons in a proper place based on its correlation with other protons which are remotely bonded. So, we took couple of examples. I am going to stop here and we will continue with this HMBC little bit more and then go to altogether a different topic tomorrow in the next class. So I am going to stop here. Thank you very much.